Alright guys, so in this video we're opening on up our topic about functions, alright? And again, so this hopefully is more of a review video for us as we kind of define what functions are, and hopefully you watch kind of the little quirky little video about functions before watching this. But the goals in this section are to determine if a relation between two variables is in fact a function, how to use function notation, talk about the domains of functions, and then finally using a little more of real life application as well too. But hopefully we all kind of know what the basic I guess gist of a function is. Let's go ahead and we normally denote a function by f. So a function f from a set A to a set B is a relation that assigns each element x in the set of A to exactly one element in the set of B. And so we've kind of thought more functions in terms of curves and in terms of a graph and things kind of like that. And don't get me wrong, that's exactly what the relationship is. All right, but it all kind of stems from this concept that if you've got a set of elements, we're going to call it A, and a set of elements, we're going to call it B, that every element x in the set A is assigned to every single one element in y. Now think about it. What do we know those sets of A elements to be, or the x elements to be? Well, hopefully we remember those being the domain, and then thus the set B, or our outputs, that we know them as a range. All right? And so let's take a look down here at the bottom, because I have four very key characteristics of a function for you. The big one we're going to talk about here is that each element of A must be matched with an element of B. And I'll show a little baby example here in just a sec to see how this matches on up. Some of the elements of B may not be matched with an element of A. That is okay. Two or more of the elements of A may be matched with the same element of B. Once again, that is fine. Two of A can go into B, no problem at all. An element of A cannot be matched with two different elements of B, and that's one of the big key characteristics. 1 and 4 are basically the same statement, just in different words. So let's take a look here real quick. I challenge you to go ahead and just pause the video for a second to see about seeing which of the following is a function here. Alright, well let's take a look here, guys. So what you want to see is that obviously that, and again this hopefully is some review for us, we want to see that every element of x matches to one y. So you kind of go ahead and say, hey, well, we have 2 going to, -3, 1 goes to 3, that is fine, 3 goes to -3, and 5 goes to 3 as well too. So we notice that different x values, all right, go to the same y value, right? So it is true that both -2 and 3 go to -3. In fact, you might sometimes kind of see it written as something more like this, where you only get 2 of them, so it would have been -2 to -3. And then we would have saw, hey, that 3 goes to -3 as well too. And then likewise here, you may see something like this. And again, that's fine. This is not a problem. This still resembles a function because every single x element only goes to one of our y elements. Well, let's take a look here. 3 goes to 4. We'll say 4 goes to 5. But now also 3 comes over here to -3 as well. So your problem in this case lies because 3 ends up going to 4 and 3 ends up going on over to -3. And so that's a problem here. Not going to have a function that we're dealing with on the right-hand side. All right. Let's continue to move on a little bit. Let's talk about the first example in which we're going to spend a little bit of time is just focusing on just some algebraic functioning. So it says, which of the following is a function of x, all right, which represents y being a function of x? Well, let's take a look. The goal is, can you solve for y in such a way that there is an x that corresponds exactly one value of y. And so let's take a look here. So in this first one that we see, part A, in part A we're looking at something that we've hopefully seen on in the past. All right. So we say x squared plus y equals 1. Let's go ahead and solve for y. So y equals 1 minus x squared in this case. And so again, you want to kind of ask yourself, all right, did we go ahead and find y in terms of x? Well, yes, we did go ahead and say that. But then did we also say that every x corresponds to exactly one y? Yes, it does. It's going to have to, because you're not going to get two solutions. All right, in an example like this, if I substitute any value into x, it's going to produce one y value. So yes, this is a function with respects to x. All right, what about part B? All right, part B, let's go ahead and solve for y first and foremost. So we get y squared. I'm going to add the x on over. We're going to root both sides. And we're going to get y equals plus or minus the root of 1 plus x. So let's think about this for a sec. Again, if I were to substitute any value in for x, all right? Well, if I substitute 1 on in, let's kind of just make a little example here. If I went ahead and substitute 1 on in, you get square root of 2 plus or minus the square root of 2. So that produces two different y values. So there's a prime example where when x is 1, y has two different values. So no, not a function of x. All right, so an example like that, we are not going to see a function of x. The next thing I want to see here real quick, guys, is just talk about some function notation. All right, function notation in this example, just making sure that once again we do remember a couple of things about function notation. The input values are x, the output we know as f of x, and then we have the equation. You know, for an example like this, you may see something written f of x equals 1 minus x squared, or whatever the case may be. So just remember that our big function notation happens in here. All right, so moving right along. Let's talk about domains. All right, let's talk about domains. Be one of the bigger parts of this lesson here today. The domain. Well, we want to kind of think about what is it. Remember, the domains were the input values. All right, we know the implied domain to be the set of all real numbers for which the expression is defined. So let's see if we can go ahead and find the domain for each of these different parts that we're dealing with in this case. So in this first example, all right, we see this in our ordered pair kind of relationship in this example. And so what do you guys think about here? Well, now all of a sudden our domains that we are dealing with are just all of those x coordinates specifically. All right, so all of our x coordinates represent our domain. So let's find all our different x coordinates. So the domain in this case is going to be the set of all x such that x is -3, -1, 0, 2, and 4. All right, so there's the domain of our particular function in this case. All right, well, what about part B? Well, and there's supposed to be a fraction bar over there. But so for part B, it's 1 over x plus 5. Well, as we can see right there, guys, you know, we can't have zeros in the denominator. So if I were to substitute 0, or excuse me, -5 into that denominator, it's going to give us 0, right? And the fact that it gives us 0 means that it cannot be part of the domain. So you may write it like this. You may say, the domain is a set of all real numbers such that x cannot be -5. And so x is an element of all real numbers, all right, such that x cannot be -5. All right, so that's what that means right there. X is an element of all real numbers The line, the vertical line, means such that x cannot be negative 5. All right. I encourage you, try and pause the video for part C and D and see if you can go ahead and get C and D on your own before we go over them. So let's take a look here at part C. So for part C, when it says define the volume of a sphere, well, let's think about this for a sec. Volume, all right, it's kind of like time. It's got to be positive, right? And so when we're dealing with the volume of the sphere, well, R is our input values. The radius of the sphere is our input values there. And so if we need it to be positive, all right, the radius can't be 0 and it can't be a negative value, all right? And so we have to make sure that it is positive or greater than 0. So we may kind of write this in a sense. Once again, R is the set of all real numbers such that x, oh, not x, I should say R, such that R is greater than 0. All right? So that kind of E means element of. All right? Means element of. And then for our last one here, well, let's take a look in the bottom or inside of the square root. And so what do we know about those roots? All right? Well, we know that those roots cannot be negative. All right? So we cannot have it be negative. So we have to figure out what values are going to keep it greater than or equal to 0. So if I went ahead and added on over on both sides, so I have 4 is less than or equal to x squared. And then last but not least, going to root on both sides. And you're going to end up seeing that we have x is less than or equal to positive or negative 2. Okay? But let's think about this here for a sec. So that's what we know that it needs to be. Okay? But if you start putting values in, all right, that become bigger than 4, you got yourself a little bit of an issue. So this is a great guide in here, but you got to use a little bit of your noggin as well too to kind of think about what else could work. Because if you throw something in that is less than negative 2 in this case, like negative 3, you get 4 minus 9, and that gives you a negative value, so you can't really utilize it. So sometimes when this happens, this could be a very good cue that it's all the values between negative 2 and 2. All right? So we're not going to use this. We're going to find all those values between. So it can be 0, so it's going to be all those values between negative 2 and 2. All right? And so I went ahead and I've written the domain in a couple of different ways on here, different notations. Set notation, it's kind of another way of set notation for B and C as well too, but using more of the symbols. And then for D, your interval notation as well. And so not overly too picky when it comes to it, just kind of know maybe if it asks in certain scenarios or another. Okay? All right, guys, that's going to pause for this video. And on our next one, we're going to go into some more real-life application.